Hey, good morning, everyone. This is Terry Albrecht. We're going to give everyone a minute or two to make sure they're online, and then I'll introduce our featured speaker for the day. So just hold tight for about another minute or so. Okay. Very good. Well, we'll go ahead and get started. Again, this is Terry Albrecht here, and we want to welcome our waste reduction partner team and a few visitors from environmental assistance and customer service as well to our presentation today. We're really excited to have Dr. Frank Leifarth, I'll get that pronunciation right, with us today, who's a professor at UNC Chapel Hill, to talk about chemistry challenges inherent to recycling plastics and plastic waste. So that's going to be a great talk for us, and definitely a nice current topic. Just a couple of housekeeping things before we jump in. We are in a webinar format, so everyone is muted as you're coming in, and we're going to do our Q&A in written form unless somebody really needs to describe their question and we can unmute you. So we're going to do most of that Q&A at the end, but maybe Frank will pause partway through to address some questions, but we'll try to do most of those at the end. So we do want to keep it interactive. I think most of you know that you can type your question in the question bar on your GoToWebinar control panel, and so hopefully that is working for everyone. You're welcome to drop me a note or send me an email if you have a problem, and you know, we can help you address that. So our topic today, I want to thank Dick Sloan for making the connection to a local state resource with Dr. Leifarth. You know, when we think about plastics, there's just so much need and opportunity and so much happening of late that we see plastics in the news. We see plastics, we see the issues with, you know, improper disposal of plastics, the challenges of recycling plastics. We're only at a, you know, 20% collection rate, probably at best. And billions and billions of tons out there to deal with. So I think this is going to be a really timely topic to hear about the fundamentals, maybe on, you know, what's there for plastics recycling, the chemistry of that, upcycling, and really how to, you know, how to improve the circular economy for plastics. And I was speaking with Frank before that, kind of sharing some of the things that we work with on as a program in WRP, and some of the promotion of our Buy Recycled campaigns, and how we try to make connections. So I think that what we're going to learn today is going to help us improve that, maybe expand our networking. I'm really excited that that Frank can meet some of the people and connect with people at this, Sandy and others I see online, and Angela, you know, with our state recycling program, our environmental stewardship initiative of manufacturers, and kind of keep building this connection. And maybe this will be a great networking effort for all of us. So so thanks for being here. A little background on Dr. Frank Leifarth. He He attended the University of South Dakota, where he was a Goldwater scholar, and he did his PhD at the University of California at Santa Barbara. Um, he received a National Science Foundation Engineering and Education Sustainability Fellowship to pursue postdoctorate studies at MIT. And since that time, his group has been looking to discover new functional material understandings, property relationships, and ultimately provide tools for chemists, biologists, and engineers to harness the vast potential of synthetic micromolecules. Professor Leifarth has received NSF Career Awards, Sloan Research Fellowships, Cottrell Scholarship Award, the Camille Dyfris Teacher Scholarship Award, and many others. And he was the star kicker on his high school. Am I getting that right? High school team or college? And leading score. So see, you can be that academic and still be a great athlete too. So with that, Frank, I'll turn it over to you. We'll keep this informal. So just you pause when you want to take some questions, or we'll take those at the end, and we'll go from there. So it's so great to have you today.
Okay, excellent. Thank you, Terry. And hello to everybody. I wish this was in person. I've given lots of these virtual seminars now, and it's always very, very weird to talk to my computer screen and not see anybody, but such is our life right now. So as Terry said, I'm a chemist. Most of the things my group currently works on are kind of, in the 10 to 15 year time frame of, as eventually being applicable to a manufacturing standpoint. But my group, I'm a polymer chemist, right? So we make polymers, and all plastics are made of polymers. Not all polymers are plastics. But I think, as a polymer chemist working on fundamental research, I think I would be negligent if a lot of that wasn't really focused on sustainability. You all know the challenges with, the ever expanding amount of plastic we use in the world, and how that has some pretty severe environmental consequences in some cases. It's, plastics also, right, lead to a more sustainable society. We wouldn't be able to drive cars as far as we do without the fuel efficiency savings of the weight reduction that plastic gives us. Right, plastics are in many important medical devices. They allow us to have sterile needles that we can, and syringes that we can send around the world and vaccinate people. So plastics are really, really important, but they also come with these inherent challenges. So we can't move on, right? We wouldn't have a society or a global population as big as we currently have without plastics. But I think it's important for all of us to think about how we can do this in a more sustainable and environmentally manageable way moving forward. So how I broke this presentation up is kind of the first half is just a broad introduction on the chemistry challenges inherent to recycling plastic. So, right, these aren't kind of the manufacturing challenges or how do you deal with these volumes of material. It's when you look at polymers or plastics on a molecular level, what challenges do we have to overcome to eventually, right, translate those discoveries kind of up length scales to, right, the manufacturing scale. And from an outcome that would be exciting for me, right, we do kind of fundamental chemistry in our labs at UNC, but I would really love to be connected more to people who are out there manufacturing and thinking about how to deal with plastic waste. So because the more connected I am to the challenges people face in the real world, the better I am able to tune the research that we do in our lab to actually solve those relevant challenges. And I find that's always a difficult disconnect to bridge with kind of fundamental science and application. But I would love if any of you that were interested in these challenges or had people that were interested in these challenges and could make connections between our lab and the other polymer scientists working at UNC. I have obviously very good connections with all those and people working at NC State and Duke. If we can be more connected to challenges on the front lines of manufacturing and recycling, I think there could be some really interesting connection points there. So I also set up this presentation, hopefully, especially the first half, as a resource for all of you to be able to read more on your own about some of these issues in the reports I cited. So I just sent Terry a copy of this presentation, and he said he will share it internally with the group, so you can all access this information in the future. All right, so just a quick summary of my group. Fundamentally, we do what's called synthetic method development. So we discover ways to make and or transform current plastics into new materials. So we kind of work in these three broad areas, and they're quite chemistry focused, as you can see. I will talk to you today about what we call polymer CH functionalization. That's essentially taking really cheap commodity materials and doing selective chemistry on those materials to break these really strong carbon-hydrogen bonds to impart new functionality. We also work in these two areas, which if you're not a chemist, may not totally interest you. But I guess the best thing, this stereoselective polymerization you show here, we can take a material a plastic that is traditionally just kind of a goopy liquid, has about the consistency of honey. We call that a viscoelastic fluid. And we can actually, just by controlling the molecular structure, so the material you see on the left and the material you see on the right are chemically identical. We just change effectively the geometry and space in how we arrange those bonds by developing selective catalysts. And we can transform that chemically identical material from this viscous fluid into this really nice semi-crystalline thermoplastic that has really good adhesion properties. So that's a fun area that we work in, and probably our most high-profile research from a scientific standpoint. But my group also combines method development with really trying to understand the mechanism of how we organize those bonds in space and how that leads to new functionality. And we do a lot of actually studying of the material properties, right? So we bend things, we stretch things, we hit things, and we see what properties they have. And we then try to understand how controlling molecular level structure can then influence those properties of bulk materials. And here is the group I work with. So that is me right here. So this is a group of mostly graduate students, a few postdoctoral researchers, and a few undergraduate students at UNC Chapel Hill. We work in Cottle Research Laboratories, and yeah, these are the people who actually do the research. I just sit in my office, and try to come up with decent ideas and help them all achieve their various career goals. So we've had numerous people go on, graduate from the group with PhDs and go on to different employment opportunities. Some, one of the students that graduated just went on to 3M to work as a research scientist. One just went over to Milliken Chemical, a chemical and textile companies down in South Carolina. One student just went to MIT for a postdoc. So a variety of career paths for these young scientists. And you can see here is all the funding agencies that we work with. So we work with a number of DoD agencies, including the Air Force and Army, a number of companies, including companies like 3M and Eastman Chemical. Recently, we started a project with, and then obviously private foundations and the National Science Foundation. All right. So a general introduction about kind of the challenges of plastic waste and what we think we can do about them. So since about really 1955, when Ziegler and Nada discovered how to polymerize ethylene and propylene into polyethylene and polypropylene, we've seen this gigantic increase in global plastic production to the point where we made about 400 million metric tons of plastics in 2018. And if you break this global production down by polymer class, you can see the largest volume polymer classes here. So as you can see, the first three materials are things like polypropylene, low density and linear low density polyethylene, mostly used in packaging, and high density polyethylene, mostly used in durable goods. So these three materials comprise a class of polymers that we call polyolefins. They're made from really simple chemical building blocks derived from the refining of petroleum. Those chemical building blocks are ethylene and propylene. And they make really strong, chemically resistant plastics that take a long time to degrade. And then we move to other high volume plastics such as PVC, PET, and polystyrene. Under this, you can see data that comes from I think actually this Ellen MacArthur Foundation report about the US recycling rate of each of these plastics. And you can immediately see a discontinuity, right? Where the largest volume plastic we make, polypropylene, is also one of the ones that is really, really challenging to recycle. As many of you know, plastic packaging is difficult to recycle, and we're getting slightly better at recycling things like HDPE. We're really bad at recycling PVC. So I see the biggest challenge in plastic waste is the fact that the plastics we make the most of are also the most difficult to recycle. You know, one of the easiest plastics to recycle is PET, and that's great. But in the end, PET is only 10% of the plastic we make on the earth. So I think a really large challenge is to figure out how to recycle all these plastics over here. And we are at somewhat of an inflection point. This exponential curve is set to continue to increase. It's estimated that about 700 million metric tons of plastic will be made by 2030. And by 2050, plastics will actually really start to compete with transportation for oil consumption. So right now, most of the plastics we get, are derived from petroleum refining and are mostly a waste product of crude oil refining for transportation. But we're about at the point where we may start using that oil specifically for plastic production, not just using the waste of refining for plastic production. So that will be a pretty big turning point in our consumption of fossil fuels. And obviously there's severe environmental consequences of all the plastic that we use and don't dispose of properly. So the goal of my research group is to provide fundamental chemical innovations that enhance polymer properties and provide pathways to more sustainable thermoplastics. I'll go into kind of this broad overview of how we think about the various problems in plastic waste. So if you look at this report from the Ellen MacArthur Foundation, you can see that of all the plastic waste generated, you can see the percentages here. About 72% is discarded, 14% is incinerated for energy recovery, and about 14% is recycled. The discarded plastic waste goes mostly to landfills. Some of it obviously is pollution. These degrade very slowly, not on the time frame of any of our lifetimes. And of course, there is, at some point, limited landfill space. Incineration, essentially you burn plastic to recover the energy, often to power recycling facilities or material recovery facilities. This is recovered as thermal energy. That is good. However, it is a one-time recovery of that thermal energy. It is a fairly inefficient way to recover energy, and it does release some noxious fumes, depending on the technology you have to filter that exhaust. And mostly recycling, I'll go into this more. It often produces lower value products. It can postpone the long-term fate, right? If you can recycle something once, that is good. You recover that energy density back into the economy. But often if that's a single use recycle, right, you don't recover it long-term. So I guess the biggest point here is plastic waste is a really complex and really, really large scale challenge. I believe that there is no magic bullet that will, help us move towards a more circular economy. It will require lots of different approaches. All of those approaches need to be at large scale because, right, that we use plastics at just a tremendous scale that is hard for the human brain to even comprehend. So we will kind of need to move forward in lots of different ways to start to solve this challenge, little bits at a time. And here I mentioned, this is more of a resource, but here are 3 really good resources on plastic recycling and some of the ways that we may move forward. So this is a Department of Energy report that recently came out. Really great work by the Ellen MacArthur Foundation, who has highlighted and really pushed this sustainability crisis into the news, and a really nice EU report on plastics. All right, so from a chemistry standpoint, we tend to think of 3 different approaches to make recycling more efficient, and I'll describe each of these in detail. But one is closed loop recycling. The idea here is you can take a polymer, which is the component of a plastic, you can deconstruct that back into the building blocks that originally made that material, and then you can reconstruct those building blocks back into a plastic with the properties of the virgin material. Essentially, you are, right, taking the, breaking apart the plastic back to the molecular level structure that originally made it, being able to use that both as a deconstruction strategy and a purification strategy. And then you have pure molecular building blocks that you can reconstruct into a plastic. We obviously know how to do that. We're very good at that. And then you can get virgin material back out. Chemical repurposing is taking a plastic and the polymers that comprise a plastic and altering the chemistry of that, ideally to add functionality that actually increases the value of that material. So some people also call this, or can call this, upcycling. But the idea here is you would create an economic incentive for recycling because you're actually making a material that is more economically valuable than the original material itself, and certainly more economically valuable than the post-consumer waste. And then biological recycling is where you allow essentially biology or often enzymes to kind of do the work of recycling for you. So if you construct a polymer that then can degrade, or you engineer enzymes that can degrade polymers that we currently use, then essentially biology can deconstruct those plastics for you back into building blocks that you could either use, or potentially these are benign small molecules that actually kind of biology can turn into CO2 and water through standard metabolic processes. All right, so kind of recycling broadly, right? PET is a great case study. There's been lots of work on recycling PET. So how feasible is, PET bottle-to-bottle recycling? So this is kind of the ultimate goal in the field is to be able to take food-grade plastic and convert it through recycling back to food-grade plastic, bottle-to-bottle recycling. This is, ideally, right? You could take a bottle, you could use it to carry drinking water, you could recycle that, you could grind it down into flakes, you could then extrude it into pellets, and then you can make it back into a bottle and use it for finished goods. The problem, as many of you know, is there's a bunch of challenges along this idealized pathway that makes this really difficult. Often you have contamination, right? Because you're getting these mixed wastes, and we're quite good at sorting them, but we're not perfect at sorting them. So you get contamination. You also have just food contamination in these goods. Often when you're grinding these materials and mechanically, right, and thermally trying to wash them and grind them, you decrease the molecular weight of those polymers in the plastic, which leads to a loss of properties. Again, if you have contamination or degradation, this can lead to discoloration, which nobody wants kind of to drink out of a brown water bottle. And often that means the bottles you would make don't meet the stringent requirements for food grade material. So actually, if you look at PET recycling, we're decent at PET recycling. We can collect a lot of material. The material we collect, we can recycle. Often this gets downcycled. I'll talk about that in a second. But because either people don't recycle those bottles, or if they do recycle those bottles, they're not in a condition to actually go and be used for further energy recovery. 70% often goes to landfills. So what is downcycling? Downcycling, sometimes called cascading, is recycling where the recycled material is of a lower quality or value than the original material. Now I want to stress, downcycling isn't necessarily bad. Often it's the way we recycle currently, and it can be really good. Two applications of downcycled materials are things like polywood. So polywood is, essentially extruded things made to look like lumber that is actually made from recycled plastic. Often this is recycled high density polyethylene. I believe a large polywood plant is being constructed or is done being constructed in North Carolina. So these, if any of you who have this furniture know, these are really great materials. They're really sturdy. They're almost completely resistant to weathering because they're high density polyethylene, right? So this is a really nice product made from recycled HDPE. Also, carpeting is a really popular material to make from PET. So this Everstrand carpeting uses recycled PET, that then make that into polyester fibers and use that for carpeting. So again, downcycling isn't necessarily a negative term. These products use recycled materials, so they're essentially not using virgin material, and they generate a lot of value for those companies and give a lot of people jobs, and they're really great products. Also, the way we make plastic means a lot of materials just have to be downcycled. About 30% of the plastic packaging, if you look at it, essentially would need a fundamental redesign before it can even be reused or recycled in a normal way. So, if you think of things like, really small wrappers that are hard to collect, if you think of things like packaging, especially multi-material, multi-layer packaging, right? This is really great to keep food fresh for a really long time, but makes recycling almost impossible because these layers are incredibly thin, often microns in thickness, and are adhered really strongly to each other. So separating those in a material sorting facility is essentially impossible. You also have uncommon materials that are of weird shapes that are just hard to sort, and other materials like this. So there's a fair amount of plastic that no matter how hard we try with current technology, we couldn't recycle, and some of that could be downcycled, which would be better than the current alternative. All right, I'll talk about upcycling in a second, but I want to talk a little bit about closed loop recycling. So this is the idea that you deconstruct plastic into the building blocks capable of reforming an identical material. This has been most successful with PET. So if you take PET and you either take methanol or ethylene glycol and a catalyst and heat this up, you can then depolymerize this PET back into this small molecule. So this goes from PET to a small molecule called BHET, and then you can actually repolymerize this back into virgin PET. So this technology has been around a long, long time. It was always considered to be not cost competitive with simple kind of downcycling of PET or simply disposing of PET. However, a few companies are really trying to push this into the market right now. I think with slightly better catalysis technology and also hoping, I don't know if it's cost competitive yet, but hoping they can, find initially smaller markets and build those into bigger markets. So BP is leading an effort that they have a number of partners to pursue PET depolymerization in this way. They're starting a plant, I believe in Naperville, Illinois, which is a suburb of Chicago. So they started building that plant, I believe, last year, and they hope to have it up and running, and I think they're targeting initially at 25 million pounds per year, if I'm correct. And you may have heard of Loop Industries. They recently went public and had kind of a kerfuffle with some hedge funds that were trying to short them, and it's a really interesting fight to read about. I'm not a big fan of hedge funds. I don't know if you all are, but I think Loop Industries has some really promising technology, again, focused on the chemical recycling of PET. A less publicized, but also I think pretty promising commercial route to do closed loop recycling is actually of polystyrene, otherwise known as styrofoam. If you heat this up above 310 degrees Celsius, sometimes you can use catalysis technology, sometimes you don't have to. This is actually above what we call the sealing temperature of styrofoam or polystyrene, and that's when it will actually just depolymerize to the styrene monomer through simple thermodynamics. So actually, you can then depolymerize styrofoam into styrene, and then use that styrene to make more valuable materials like maybe an ABS or SBS thermoplastic elastomer. So again, this is being commercialized by a number of companies. This INEOS Styrolution technology is building a plant in Antwerp, Belgium to do this. And this company, I think it originally started in the US over in Oregon. I think it's now relocated to Sweden, but Agilix is also pursuing this polystyrene depolymerization technology. This technology works really well. I think one of the challenges for this technology will be actually just collecting the styrofoam, because a lot of styrofoam is EPS waste, right? Expanded polystyrene foam. And the problem with that is that it actually costs so much to transport that material, because it is so light and has such a low density that right, it fills up, let's say, an 18-wheeler with actually not much material because it's so light, and then you're paying so much in transportation and gas costs that it's not actually efficient to relocate that styrofoam around. So then it actually, maybe densification technology, that is distributed will be important to make to push this solution forward. Talk just a second about biological recycling. I see biological recycling fitting into two general areas. The first is in the use of polymers that can be degraded either by enzymes or maybe even just kind of by composting, such as polylactic acid. So polylactic acid is a pretty high volume commercial product made by NatureWorks. It is often called Ingeo Bioplastics. I think the place where you may have seen it most is in like compostable cutlery and cups. Actually, UNC has all these compostable PLA cups in our dining facilities. So again, these you can ideally can be composted and eventually degraded and metabolized back down to CO2 and water. That obviously can be used by plants to reform glucose, and we get polylactide by the fermentation through engineered bacteria of glucose to lactic acid and eventually the monomer lactide that can be repolymerized to polylactic acid. So again, this is a commercial product made on, I think, hundreds of thousands of ton scale per year by NatureWorks, which is a company, their facilities in Nebraska. I think the company's based in Minnesota. So polylactide is a great sustainable material and obviously used. There are a few challenges for it, however. Unfortunately, the material has subpar properties. So honestly, if PLA had great properties, it would start to displace things like polyethylene, and that would really be great. But unfortunately, it just doesn't have those good properties, so that really limits its applications. Consumers don't want to use it for many things. Unfortunately, it's found that while it degrades in laboratory tests, it does not degrade under typical landfill conditions all that fast. So if you just put these things in a landfill, they'll still sit around for hundreds of years without degrading. So the rate of degradation is too slow. And that is the same even in industrial composting sites. So if you can divert this waste to industrial composting sites, that's great. But actually it degrades too slow in industrial composting sites to really be economically valuable. So ideally, we could create, right? I think there's one way to biologically recycle polymers. Create a polymer that can be recycled by biology. But ideally, we create a polymer that has better properties and composts a bit faster. But still, PLA is a great material. I do really like it. Another way to biologically recycle materials is to actually engineer enzymes to cut up polymers. So this is PET. This work has been going on for a long time, but actually a recent Nature paper came out that is more and more viable. So what they found is they engineered an enzyme that could degrade bottle-grade PET, so this is crystalline PET, in water at pH 8 at 72 degrees Celsius. So this is, and you can see the depolymerization of bottle-grade PET at a reasonable rate. So after about 12 hours, you depolymerize about 90% of that PET in that water. So right, this has been a field that's been going on for a long time. I think it's really interesting that they now have engineered an enzyme that's thermally stable enough to heat this up to 72 degrees Celsius. Obviously, when you want reactions to happen faster, you want to heat them up. However, if you heat enzymes up too much, they degrade, right? So this enzyme is actually engineered not only to depolymerize PET, but also to be as thermally stable as possible, to be able to heat it up to a temperature where you can get pretty reasonable rates of depolymerization. So this is certainly not ready for prime time, but I think it's a really interesting research avenue. And the last part of my general topic, I'll talk about upcycling. So upcycling is the use of plastic waste as a feedstock for the synthesis of value-added products, whether they're polymers, molecules, or materials. Again, the idea here is to create an economic incentive for recycling. So this is a review I helped write and is currently under peer review. So typically, right, we go from petroleum to monomers to polymers to plastic products, and I just kind of described the three ways the three fates of those plastic products. They could be landfilled, they could be incinerated, I guess they could be pyrolyzed, or they could be recycled. Another avenue that's kind of new is we could do a form of chemical recycling that is upcycling, where we can make a new polymer, a new molecule, or a new material. And before I go into this too much, I did want to point out a small company in Durham, North Carolina that I work with quite a bit. So this is kind of my one connection to manufacturers and people trying to solve this problem. So this company is called HighCube. They are focused on zero waste initiatives for plastics that are difficult to recycle, and they extend their lifetime through interesting product development. So right now, HighCube is really focused on polyethylene and polystyrene, and works with a number of pharmaceutical companies to take their waste, densify it, and turn it into other products, such as higher-end furniture, dog beds, and a number of creative things that Bradley, who is the CEO there, is working on. But if anybody's interested in contacting HighCube, again, I have their website there, and I'm happy to make a connection if you want to go through me. So what is an example of upcycling? Here's a nice example of upcycling that was published a few years ago. This group took BPA polycarbonate. This is often used in construction and automotive applications. It's made on a few hundred tons a year, and they could take that in one chemical step through catalysis. So I guess BPA polycarbonate is also used as CDs or DVDs or Blu-ray discs. Obviously, these are becoming less relevant, these days. But they could take this in one step using a monomer and creative catalysis to a polysulfone. So a polysulfone is a material that's used in water purification membranes and high temperature automotive applications. This material is much more economically viable than this BPA material. So this is a really nice chemistry example of taking, a cheaper polymer that currently isn't recycled and actually making it into a higher value polymer that has a really long use time. Another example of upcycling that I'm interested in is compatibilization. So compatibilization is when you take a mixed waste stream, and typically these mixed waste streams, right, on a kind of micron scale are composed of these two plastics that don't mix with each other. So usually one plastic forms a continuous phase, the other plastic kind of forms these large droplets. And if you just take this material and look at the properties of this material, it's usually very brittle. And it's brittle because, right, you have these huge droplets of one plastic in another. There's no interfacial adhesion between those two plastics. So when you start to apply a strain to that material, it breaks really quickly at that interface and just shatters. However, if you can compatibilize those materials, which means you can add often an external component to stabilize that interface, those droplets of one polymer in another will become much smaller. They'll become much more dispersed. Often you're adding something like another polymer that can kind of stitch those interfaces together. And now this compatibilized material can have really great properties. Often, it can extend to long lengths. It can be really tough. It can be actually a valuable thermoplastics. So this compatibilization, this upcycling by compatibilization would be really relevant if you want to, for instance, actually try to recycle multi-layer packaging, right? You can't separate these things on the macroscopic level, these different layers. But if you could add a compatibilizer to compatibilize all these three things together, you could potentially extrude a valuable thermoplastic from this multi-material packaging. The same could be said for mixed plastic waste post-separation. So post-separation, often in a material recovery facility, you have, let's say, a sink fraction that is composed of a lot of different plastics, or you may even have a cut of one of the float fractions that contains, let's say, polyethylene and polypropylene together, right? If you can compatibilize those materials selectively, again, you can get a higher value material out. So here's an example, this science paper that was published a few years ago. In this case, isotactic polypropylene, high density polyethylene. This is these are common materials that after separations are found in a mixed float fraction. So these scientists found if you add a really small amount of this high value compatibilizer, even about half a weight percent, you can dramatically improve the properties of this blend. So if you take polypropylene polyethylene blend, this is what we call a stress strain curve. So stress is effectively, you can think of it as strength, and strain, you can think of it as percent extension. So if you look at this blend, this is actually a zoom in of this part here. You get to about 20 megapascals right, strength, but then you can only, it's a really brittle material, so you can only extend this about 10% of its original length before it shatters. If you look at polyethylene, right, one of the reasons it's so valuable is because it's reasonably strong, but you can extend this out to about 800% of its, so 8 times its original length before it'll break. Polypropylene is stronger than polyethylene, and you can extend it out to about 3 times its original length before it breaks. So if you compatibilize these materials, you can actually get to compatibilized plastics that have the properties in between that of polyethylene and polypropylene. So if you add 0.5% compatibilizer, you can see, or if you add 1% compatibilizer, that's better. You can now extend this mixed material out to about 5 times its original length before it breaks, and it has a strength that is higher than polyethylene but lower than polypropylene. All right, so that kind of concludes my general overview of different plastic waste management strategies. So I'll talk a little more about the work my group is doing, but I thought this would be a good place to pause and take any questions or discuss any of the things I presented previously.
Well, great, Frank. This is fantastic information, and I know our group is soaking it all in. There's just so much here to learn more about and to make more connections. So I want to invite folks to type in any questions for Frank right now, and we can address those, or in the interim with a lot more to come. So any questions, anyone? And if you want to ask that question, if you want to type in that you have a question, I could unmute you. So, let me, all right. Hey, Richard, or Dick, excuse me. I'm going to unmute you for a minute. Oh, maybe I'm not. Okay.
There we go.
Oh, great.
Yeah.
Dick, go ahead. Do you have a question?
Well, first, Frank, thanks for doing this. First time I've seen your image. So
there you go.
Yeah. Maybe this question is a little bit early, perhaps, but eventually I'd like if you have any thoughts on what any of us in WRP or with the state offices can do to help assist you in your efforts or your lab's efforts, getting the word out on some of the cool things that are going on and some of the time frames. We're here, and if we can be extensions for you, I think many of us would like to do that.
No, that's great. I'm really happy we made this connection, and I think initially the best thing would be if any of you have challenges that people are dealing with on the ground and or materials recovery, a tour of a material recovery facility for me and some people in my group would be really valuable. Learning what different challenges manufacturers or material recovery facilities are facing, that could kind of help direct my thinking and my research towards solving some of those challenges, right? Because I think me being stuck in what some people call the ivory tower, right, sitting in my office, I can think of a million ideas, but I often don't know if those ideas are useful or not, because I don't know the real on the ground nitty gritty problems that people are having.
Okay. Great. Thank you.
Yeah, that is great. Thanks so much. We really want to foster those connections going forward. So, Dick, thanks for that. We have a number of other written questions coming. So this is from Jan Harden. She's our solid waste management with Waste Reduction Partners, and she says, can you share any more about your work with 3M or anything specific that you're doing with 3M?
So 3M, my relationship with them currently is, well, I have a lot of friends that work there, now a former student that works there. And I received the 3M Non-Tenured Faculty Award, and that was in the area of thinking about how to make fluoropolymers more sustainable. So that really eventually led to my group's work. And I didn't put anything in this presentation about it, but we have made a resin that purifies PFAS from water. So many of you may know this is a big issue in North Carolina, especially with the Gen X, pollution issue for especially Wilmington, but actually kind of all through the Triad and the Triangle and the eastern part of the state. So we've made a material that can be packed into resins and can remove PFAS from water better than current technologies, so ion exchange or activated carbon. So I've given numerous talks at 3M and been in contact with them, and as we move this material towards larger scale applications, as we figure out how to make it economically, right now its performance is great. We're working on how to make it economically viable. 3M potentially could partner with us or even implement some of those resins at some of their sites to make, again, their fluoropolymer production more sustainable. So this is in sustainable plastics, but kind of in a different area.
Great, thank you, Frank. The next question comes from Dave Lowles. He's an engineer with our program, works on a lot of industrial byproduct reuse and new product development kind of things as well. And he's asking if you have any comments about nylon 11 or 6.6, just in this kind of background of uses. And
yeah, I mean, I haven't thought of those. I haven't thought of nylon a ton. I don't know anything about how efficient kind of the recycling sorting of nylon is. Where I have thought about it is, a mixed waste stream is actually HDPE nylon. And so if you think about, there's a lot of efforts in cleaning up ocean waste. And a large portion of ocean waste is what is called ghost fishing nets. And fishing nets are made of either polyethylene or nylon. When you collect fishing nets, you inherently have a mixed waste stream. So if you can figure out ways to compatibilize polyethylene and nylon, and we think some of the chemistry we're developing that I'll tell you about can do that, we could potentially create, pretty interesting materials. We can also, some of the technology we're developing could also potentially toughen nylon, right? So an additive that you put in at 5 weight percent that could toughen nylon and give it a little better properties that way. So I think that nylon is actually from an upcycling standpoint a fun polymer to think about, because you actually have really interesting functionality you can work with in those amines and amides in the backbone. But that's kind of the extent I've thought of it.
Super. All right. Thank you. Next question from Conrad Meyer on our group. He's a chemie, does a lot of work across multiple areas, and he's asking, is it feasible to separate the layers of a multi-layer film using a solvent process? And that
maybe. So there's a process that Procter & Gamble developed called PureCycle. That now they've spun out a smaller company on. And they have developed a way to selectively solubilize polypropylene from polyethylene, I think using supercritical propane as a solvent. There are potentially ways, but I think that's really, I mean, as you can see, supercritical propane is not a common solvent, right? So that's a really specific process that I don't know if it's economically viable. So potentially there are ways, but the problem, again, the problem kind of comes down to what I said in the first slide. Polyethylene and polypropylene are the two polymers that are made at the highest volume, and they are the only solvents they're soluble in are really harsh, really environmentally unfriendly solvents that you have to heat up to 150 degrees Celsius to even get them soluble. So this is actually why a lot of people don't work with them, because they're so hard to work with. So I think in those, I think it's just going to be really tough from a cost, and you probably end up being less sustainable because you're using such harsh halogenated solvents in a lot of cases.
Okay, great. That's a good background. Yeah, we've got lots of questions, Frank. Are you okay just to run with some of these? Okay, so team, we're gonna, we were scheduled to go to 11:30, so we'll probably need all that time. But I think these are good, and lots of good input. Okay, next one from George Turgay. Is there any possibility of using photochemistry working with polymers?
Yeah, and we've looked at that a little bit. The problem with photochemistry is it's just so hard to scale up. So if you just think of the standard Beer-Lambert law, right? A photochemical reaction is dependent on the path length of the reactor you have. So you really need short path lengths to get a photochemical reaction to be efficient, because that efficiency will decrease the larger path length you have. The problem with the short path lengths means you have a small reactor, and nobody cares about a plastic unless you can make like a metric ton of it. So to scale up a photochemical reaction for a bulk plastic solution is going to be really hard. Where photochemistry is used often is in things like 3D printing. I think 3D printing has a lot of potential, but also a lot of sustainability challenges that it has to really think about. And then also in photolithography. So if you just need to functionalize or change the surface of a plastic part, then you can do that with photochemistry, right? But to actually use it on a bulk plastic, I think that is probably not possible for the scale at which we want to use plastics.
Okay, hey, thanks for that. Next question here is from Greg Goodman, a little bit more logistical oriented, and the question is, can high volume plastics be mechanically pressed, maybe to the point of melting, to help decrease the transportation costs?
Oh yeah, for sure. So actually, that HighCube recycling, one of the things they do is they take EPS waste and grind it and densify it. So densify just means essentially melting it. So under pressure and heat, right, they melt it into flakes that they can then are much more dense, and you can actually it'd be economically viable to then ship it somewhere. I think what we have to do there is we have to think of a more distributed manufacturing workflow for that, because you would ideally need that densification technology distributed close to the sites where all this waste is being produced, which is different than kind of like one of the problems with plastic manufacturing and waste is very centralized. So polyethylene and polypropylene are made in a few places around the world. They're then shipped often across oceans to then be extruded and injection molded. Then they're shipped across oceans again to consumers, right? It's a really inefficient manufacturing philosophy.
Okay. And I think we'll take one more here, and then we'll save the rest for maybe at the next pause. This comes from Kent Davis, but he was asking for, I think, some other commercial examples of the compatibilizers of those forms of plastic. So that looks like a really interesting way, but are there some commercial examples of what's produced from that you could share with us, or is that still kind of in the development phase?
No, there are definitely commercial examples of polymer blends. So here's a few. So, a lot of them that I know about, this is an area that I'm somewhat weak in because I'm not an engineer, so I don't always know all the kind of commercial applications of things. There's a lot of polymer blends used in tire manufacturing. So tires are incredibly highly engineered, multi-layers of materials, and in those multiple layers of materials there are a number of polymer blends. Often these are blends of butyl rubber. So butyl rubber is super important because it is the most gas impermeable material known to man. So that's why you can fill up your tire and it won't go flat. And then the many layers of a tire, has a bunch of composites that toughen the material. So composites also often have compatibilizers in them to make sure the filler mixes well with the polymer. So many layers of a tire are that. Other composites like carbon fiber composites, depending on the continuous phase material, they will have compatibilizers in them. There are probably many. If you just Google search polymer blend, you could probably find more that I don't know about.
Super. Hey, well, Frank, thank you for addressing that broad breadth of questions. And we're going to let you get back to your presentation right now. It's 10:55, so we've got about 35 minutes. Just FYI on timing.
Yeah, this last half should go pretty fast. All right. So I just have to show you. Don't be too scared. I'm going to show you some chemistry. I will try to make it as easy as possible, but I do need to show you some chemistry and some of these, right, kind of skeleton sticking drawings to kind of describe what my group does. But I'll break it down with my words as simple as possible. So again, my group, we've identified polyolefins as really the challenge that needs, like, if we need, right, we're not going to create engineering advances in my group to solve the plastic waste problem, but we can create fundamental chemistry advances. And the area that we think that needs to happen is polyolefins. Again, because this chart right here, right, they're the highest volume wastes, and they're the wastes where the worst at recycling. So polyolefins are polyethylene and polypropylene. If you look at the just chemical structures of these, any point at which there's just a point here, this is carbon. I could write a C here if you wanted. But essentially polyethylene and polypropylene, the thing to know is it's only carbon-hydrogen bonds, right? There's no oxygen, there's no nitrogen, there's no other functional groups here. So that makes these things really inert, incredibly chemically stable. Carbon-hydrogen bonds are one of the stronger bonds known. Makes them insoluble and really difficult to work with. So they're really great as materials, again, because you can take, right, your polywood, which is high-density polyethylene, you can put that outside for years and it won't degrade. It will be excellent, right? It's really chemically stable. So that's great as a material, but it's really bad as for a recycling strategy, because again, it's really hard to break these things down, right? So if you look at the advances in polyolefin structure and properties, this really started in 1953 and 54 with the discovery of the Ziegler-Natta catalyst. Both Ziegler and Natta won Nobel Prizes for this, and this really allowed us to scale up the production of polyethylene and polypropylene. An amazing thing is the polyethylene catalyst was discovered in 1953, and by 1956, a factory was already built and producing this material commercially. That's how amazing the advance was, and again, clearly valuable. So since then, you know of polyethylene in many, many different forms. So this is a really simple chemical building block that, because we've advanced, really amazing advances in catalysis, we can now make polyethylene, right, that is a durable good. We can make a polyethylene elastomer. We can make a polyethylene compatibilizer. We can make a polyethylene that has the same properties as engineering polymers. So by figuring out how to connect these different building blocks in different ways, we can make a whole bunch of materials. However, what we can't do with polyethylene is make functional materials. So really the two advances on that, adding kind of polar groups onto polyolefins, the two advances in that were really in the 1960s, and nothing has been commercialized since. So there actually, in 1995, there was a big advance by Brookhart, who was a professor at UNC and is now an emeritus professor at UNC, just an incredible scientist. And he worked with DuPont for a long time, but still, despite kind of this advance, nothing from here has ever made it into commercial products. So we've kind of been stuck with this technology from the 60s to make these kind of more functional polyolefins. However, we would really want to make functional polyolefins because, if you look at what polyethylene and polypropylene are currently used for, they're kind of, durable goods, disposable, single-use items. If we can add that functionality in a selective manner, we could start to take these, cheap polymers and ideally even waste from these polymers and make higher value materials like composites or backings for electronics, these polymer blends, these adhesives. So what my group has done is what we call, our approach is we call it CH functionalization. And we call it that because we're taking carbon-hydrogen bonds, which are traditionally very strong, and we're actually, you can see here kind of in the scissors analogy, cutting them and placing new groups onto that polymer. So by doing this, we want to expand the property space of these really widely available and cheap materials that are already made on millions of ton scale, right? So our starting materials are widely available and in, like some of the cheapest materials known to man, right? So if we can develop this chemistry, there might be some real interesting economic opportunities. Ideally, we want to discover new material properties and use this technology to upcycle plastic waste. So our kind of vision here from, this is a new slide I added, is to take material directly from a material recovery facility. One of the things my group is really interested in is compatibilization. So can we take, especially maybe mixed waste material from a material recovery facility that is either bound for incineration or will go into really low value products? Can we add a compatibilizer or a reagent that will compatibilize things in situ, put that directly into an extruder, extrude that material, injection mold it into a high value part, right? So can we take waste and in a simple workflow, use technology that's already used to process and mold polymeric parts to get a value added material? So this is the chemistry part of the talk. I'll go simply through this. So BDFE is bond association free energy. So this is just an energy component. It is just essentially how strong a bond is. So if you look at polypropylene, again, highest volume commodity polymer, almost none of it is recycled. You can see there are 3 CH bonds, and they all have very high and very similar bond association, bond energies. So 100 kilocalories per mole is a really strong bond. Usually, if we want to do a reaction with these materials, we will put these materials in an extruder with a peroxide, and this peroxide will create a radical that can react with one of these CH bonds, but that radical only has a bond association free energy of about, anywhere between 9 and 4 kilocalories per mole difference between these. So if you're trying to do a reaction with a material that doesn't have a much higher bond strength than the bonds you're trying to react with, you essentially get, there's not a large thermodynamic driving force for that reaction to happen. So what happens is a bunch of reactions you don't want to happen. Particularly, this is just a mechanism, you don't have to pay attention to this. The problem here is this beta scission. So this beta scission means that every time you're trying to add a functional group to polypropylene, you're actually breaking that polymer chain in half. And if you do that a few times, that polymer becomes an oligomer, and those oligomers don't entangle and don't have good properties anymore. So this has been the fundamental challenge really since the 60s for recycling polypropylene, is every time you try to do anything to polypropylene, it falls apart. And this is one of the reasons why only 1% of it is recycled, because if you try to mechanically recycle that too many times, you try to add additives, it will just fall apart and the properties will not be good. So our hypothesis from a fundamental chemistry standpoint is just to use a radical to react with polypropylene that has a much higher bond strength than the radicals people previously used. So we could use what is called this amidyl radical. And this is actually cool because it's a collaboration with Professor Eric Alexanian at UNC. So his whole research program is focused on pharmaceuticals. So developing reactions that you can do on pharmaceuticals to enhance their properties. So we actually saw in this chemistry he was developing for small molecule pharmaceuticals, we saw potentially there was opportunity with the concepts he was using to use this on polymers and plastics, and especially plastic waste. So this has been, this is one of the great things about being at a university where people are doing a diversity of research. You can make those connections. So we took this reagent, and essentially the workflow of this is we add a branched polyolefin. This is polybutene, but it's similar to polypropylene. And this reagent, this was done by a graduate student in the group, Jill Alty. She's originally from Virginia. She went to the College of William and Mary. She came as a graduate student to UNC, and she just got her PhD 2 months ago and is now at MIT as a postdoc. So she took this reagent. This is actually just a solid powder, right? So you take a ground up polymer, you kind of sprinkle in a bit of this solid powder, and what you're able to do is add this chemical functional group onto this polyolefin. And the really cool thing here, you can add a variety of densities of this functional group, but we use this characterization technique called size exclusion chromatography. And if you were breaking those polymer chains like in the previous technology, you would see a really large peak come up right here at about 37 minutes retention time. But what you can see when you add a variety of amounts of this chemical functional group to the polymer, you don't see this peak arise at 37 minutes of retention time in any of these instances. And that's a really big deal because this is one of the first technologies that uses this radical chemistry to functionalize something like polypropylene that doesn't degrade the polymer. So that means the properties of this polymer will still be just as good, but now it'll have this additional functional group on it. We then went on to do this chemistry on commercially relevant polymers. So we did it on linear low density polyethylene, which is, the predominant material used in plastic packaging, low density polyethylene, and isotactic polypropylene. And we even did this chemistry in an extruder. So in this case, we didn't use any solvent. Again, this reagent is a powder, this polymer is a powder. We mix those two polymers together, we put them in an extruder. I'm sure many of you are familiar with extrusion technology. This is how polymers are pelletized and processed industrially. This is a picture of our little lab scale extruder we have. And what you can see again is this is the polypropylene on the left that we put through the extruder. This is our material on the right. So what we did is we added this chemical functional group onto the polymer. And you can see again here, this is one of these size exclusion chromatograms. So, you may see in polypropylene a little bit of an increase in these lower molecular weight fractions. But if you would do this, we actually did this experiment with just one of those traditional peroxide radicals. You see this whole peak shift down here. So that is obviously not happening with our material. And this was really a huge advance in the field. The cool thing is so now we have a bunch of this material, right? We can compression mold it into a shape. We can use that shape and pull on it essentially until it breaks to do the stress strain experiment. If you look at polypropylene and our material, you can see our material behaves very similarly. You can stretch this material out to about 4 times its original length before it breaks. And the strength of our material is a little lower, but we would expect that because we added this functionality. So the strength is a bit lower, but with this functionality, again, it can act now as an adhesive or a compatibilizer much better than polypropylene. So to test that, we did this adhesion experiment where we essentially just glued 2 glass slides together with our new material and pulled on that until it broke. And we found the addition of this chemical functionality improved the adhesion strength of our material 2.5 times compared to polypropylene. So we've created a material in an extruder just by kind of sprinkling in a little bit of our reagent that has similar properties to polypropylene, but now adheres to materials 2.5 times better. So that was really exciting. Moving on from that, one of the challenges we were facing, this is a chemistry challenge, is that, right, we would create these reagents, but every time whatever was connected to the nitrogen of our reagent would then have to be connected to the polymer. And this limited the scope of what we were doing a lot, and actually limited the types of materials we could make that people would be potentially interested in. So we came up with a new way to do a similar reaction, where actually we could have a choice of anything we wanted to add to a polymer, and we engineered this reagent in a way so actually whatever we added into this reagent, to this reaction, would be connected to the polymer. So we call this a universal any substrate, any function approach. So now again, we took linear low density polyethylene, that is a polyolefin here. I'm not showing you the actual structures here because we're still getting IP on these specific chemical reagents. And we could make carbon-carbon bonds to the polymer, carbon-nitrogen bonds to the polymer, carbon-halogen bonds to the polymer, carbon-sulfur bonds to the polymer. And again, this is a size exclusion chromatogram. We don't see at low retention times, or at high retention times, I'm sorry, this peak arising. So this is incredibly selective at adding this polar functionality to the polymer and not degrading the polymer. We even worked with our partners at HighCube Recycling to get post-consumer polyethylene from packaging forms and use that in our reaction. And we're able to see, again, we could add those chemical functional groups in similar efficiency, even using post-consumer polyethylene. And we saw, by different spectroscopic techniques that there were common additives that are typically found in post-consumer polyethylene. And again, these additives actually didn't interfere with the chemistry that we were developing. So to showcase these materials, we wanted to make materials that are commercially relevant currently. So there's a class of materials called ionomers. Their trade names are things like Nucryl, Surlyn, and Elvax. And these are high value materials. If any of you golf, you will know Surlyn because Surlyn is often the outside casing of a golf ball. So just by knowing that, this is not typical polyethylene. This is incredibly strong, incredibly tough, incredibly resilient material, right? These are really high value materials. However, there are some limitations with ionomers. This was technology developed in the 60s. It creates a linear low or a low density polyethylene architecture, and essentially you can't use Ziegler-Natta catalysis to do this. You have to use these really special conditions where you're pressurizing these reactors to 1,000 to 3,000 atmospheres of ethylene pressure. So this is, a really specialized process-driven approach to make these materials. We want to make these high-value materials not by using thousands of atmospheres of ethylene. We want to make them from waste. So we showed we can do that by first using our reaction to add this primary bromide and then making an ionic species here, this imidazolium ionomer. And again, you can see the material just visually changes a bit. When you press it, it has increased clarity. But the real key here is the linear low density polyethylene that we made this material from. You can stretch that about to 3 times its original length before it breaks. By making this ionomer, we make a much tougher material that actually is much more elastic also. So now this has kind of this soft yield point, but now stretches out to about 7 times its original length before it breaks and has this really high toughness. So again, this is some of the things we think we can do, right? By, again, taking a commodity material, potentially even waste, putting in some of our reagent, running it through an extruder, you can have this dramatic change in properties. And ideally, that change in properties leads to a material that's more economically valuable than the current material. That's our vision. I will say currently that because we're doing fundamental chemistry, the reagent we make is way, way too expensive to actually implement this. So the properties we're getting out are valuable. We need to, in the future, find funding to work on simplifying this reagent and making it actually cost competitive. And also, we need to make sure the byproducts of this reagent aren't toxic, right? There's lots of kind of translational research yet to do, but I think just currently, the concept that we demonstrated wasn't possible using previous technology. So we now have a new technology that can do this, and now we're thinking about how do we make it economically viable? How do we, think about the sustainability aspects, et cetera. And ideally, how do we use this for compatibilization? So I told you about a compatibilizer, right, where you could actually add a separate material. What we want to do with our chemistry is, can we add our reagent to a polymer blend and actually have that reagent selectively just do reactions on that interface to compatibilize blends? So this is potentially a really general way to do this. So again, if you have mixed waste that you maybe inherently get from a materials recovery facility or you get from multi-layer packaging, can you add our reagent to that material to make high value thermoplastics directly? All right. So I still left a few minutes for questions here, but again, here's my group. And that's, one of the, I think the most relevant project that we're working on kind of in the area of thinking about plastic waste is developing these reagents that you can put into plastics and use, I think that a really valuable thing here is you can use infrastructure that's already implemented right at plastics manufacturers or potentially even some recycling facilities, i.e. extrusion. So you can use that kind of technology, the infrastructure that's already installed. You don't have to retool everything. You don't have to spend a bunch of money up front. All you would hopefully have to do is use a reagent that we could develop and continue to optimize to get these large changes in properties. So this would be an upcycling approach.
Well, great, Frank. Thank you so much. What just incredibly fascinating information and an optimistic outlook on how to deal with things like mixed waste from a material recovery facility, because that's been such a challenge for so many. We've lost so many Chinese markets where that low value material went, and now we're trying to figure out, well, what can we do with it, and where can it go? So so I want to encourage everyone to go ahead and type in your questions. I do want to ask one question on that. So it looks like you have some really promising chemistry. Some congratulations on those breakthroughs. How do you see contamination being dealt with in something like the compatibilization of mixed waste into, a blend at, let's say, a material recovery facility, because that contamination level is so, I mean, I'm talking about like non-plastic contaminants there as well. Has there been thought in that, or are you still kind of at the forefront of just trying to make those chemistries work without thinking about, all the variability and cleanliness and quality of those mixed plastics?
Yeah, I mean, that will be a challenge moving forward for sure. I think the inherent advantage to our approach is we are using radical chemistry. So a radical is the reactive intermediate that we're using. And, the great thing about radicals is they work in the presence of water, right? They work, biology uses a lot of radical reactions. So while they are very reactive intermediates, they don't get quenched by kind of water or other common things in the atmosphere, which is very good. They are sensitive to oxygen, but actually in an extruder, in an extruder kind of there's not a whole lot of oxygen. There's not ways to transport oxygen. So we found that actually, and this is pretty well known, in an extruder, it's oxygen is at a pretty low loading, and these reactions can still work. So I think the approach of using the type of chemistry we're doing that is inherently pretty amenable to some contamination is good. From a compatibilization standpoint, right? Essentially, when you compatibilize things, I show a really simple 2-component compatibilization. If you have contaminants, that is actually kind of a 3rd component, right? Or 4th component, or depending on how many contaminants you have and the levels of those. So, at a certain point, a mixed stream is probably too dirty to have chemistry work on it. A good thing about the reactive compatibilization that we're trying is typical compatibilization, where you add an external, let's say, block copolymer. You need to know pretty well the components in that stream and the percentage of each different plastic in that stream in order to select the right compatibilizer. The fact that we're using chemistry to do this, actually the chemistry kind of does all that optimization for you, so you don't need to optimize things, as well. So I think that's an advantage. And then I think better sorting technology is continuing to come out. So hopefully, as I think again, this is there will have to be many advances in many different areas to keep chipping away at this problem. But better sorting technology will continue to help that, right? So I think and then at some point, right, there's always going to be some kind of probably sink fraction that it's better to incinerate.
Right. Yeah. Very good. Well, hey, thanks for addressing that question. Next question we have from Dave Lowles, and he's asking if any of your research approaches could be used to compete with PEX. So I think he's thinking of PEX hosing and tubing and things that are used in plumbing.
So are you talking
application
recycling PEX or competing, like creating a product that could compete with PEX?
Well, let's see. It's saying compete, but Dave, I could unmute you if you'd like to try to ask that question. Dave, are you there?
Okay.
Go ahead, Dave.
I was thinking of using a recycle stream of material to compete with PEX. It had all the same characteristics for the water use at homes and stuff, but it doesn't need to be cross-linked.
So I think PEX, for those of you who don't know, is cross-linked polyethylene. It is often used to replace copper pipe for like running hot water around your home because it's more thermally stable. If you're going to use, so I could imagine, and some of the chemistry we're developing could potentially be used to take a post-consumer material and cross-link it into PEX. That would maybe be beneficial because PEX is a higher value material than, let's say, HDPE. The idea about, I think PEX I think to get the properties of PEX from polyethylene, it really relies on that cross-linking. So at least in the near term, I think you're going to have to cross-link, right? You're going to have to make a thermoset to get the high temperature properties required. And then PEX, what challenge with PEX is that because it's a thermoset, it's going to be really difficult to recycle because it's not going to be soluble. So I think recycling PEX itself will be difficult. But taking post-consumer materials and turning it into a material like PEX, I think is feasible.
Thank you.
Okay. Does that answer that, Dave?
Yes.
Great. Thanks, Dave. Okay. One other question. This is a little different, but I think it's a background question about the use of plastics in different forms of packaging. And so this is a question from Scott Pfister, and he's thinking, his question is, if we think about biologically created packages like peels or skin or shells or that kind of things, is there something that we can learn from how those materials, in terms of how they are deconstructed, that might help in your research, or even how they are, I guess, digested in some way?
Yeah,
kind of
I mean,
biomimicry kind of maybe question there.
Yeah, no, that's definitely the idea of biomimetic kind of chemistry or engineering deals with those things. Yeah, there are definitely lessons to learn. There are people thinking about that. Often biology is just, they're much better chemists than we are. So often those materials are quite complex, and their complexity serves multiple functions. It both allows them to pursue the function that they want to, but also, they kind of engineer in a end-of-life fate. So I think, the whole plastics industry, we're trying to figure out how to, be even 1% as good as biology, right? So we now make materials that are useful, but now can we engineer in the end-of-life fate at the beginning of the production of materials? So one area I chose not to talk about here is like the creation of new materials that both compete with current petroleum-derived materials and, have a defined end-of-life fate. That is a whole area of research that would just have filled this up too much. But I think in that area of research, maybe that's right, because that kind of takes, I think that would require a fundamental redesign of the materials we use. But we could start to try to take a step closer to biology in that way.
Great. Well, very good. Any other last questions from anyone? If you want to type those in. And Frank, if you would go to your last page just so you have your email address up there again one more time.
There, yeah.
Yeah, perfect. So, not seeing any additional questions come in, I really want to thank Dr. Frank Leifarth for this really intriguing presentation. I mean, I think that this is so amazing to hear about your work and to hear how you're focusing on these key needs that we have, that we're seeing in recycling and use and on the plastics end. So this is really exciting. And I think that we're gonna, from this point forward, I think several of our folks are working with clients that there may be applications you may want to know about or know that there's a need there and work on, and also the connection with our state recycling program. I think they may be reaching out to you for future needs here, because this is really great. So I want to congratulate you on your work and some of the breakthroughs that are happening, especially with your students, and seeing them move forward must just be incredibly rewarding. And this has been really, really informative to our group today. So I hope we can kind of continue our relationship and work together, and maybe helping connect to other industry needs with the kinds of development research that you're doing. So thank you so much again. For our team, I will share Frank's presentation with you and contact information, and that'll be kind of step one in our going forward. So so thank you so much. Any other things you'd like to share?
No, I would just like to say, yeah, thanks for inviting me, and I hope this spurs I hope this is the start of a relationship. you know, I and my colleagues think about applying for, right? I've applied for grants through the DOE and the NSF that, you know, are really bolstered by partnerships with groups like yourself and other people actually at materials recovery facilities and things. So, you know, the connections that I hope we can make from this will, I think, be beneficial from a just intellectual standpoint of learning more, but also hopefully we can actually create partnerships that lead to grant funding in the future that kind of help the state more broadly.
Yeah, absolutely. We'd love to be a part of that or be a connector or a network component of that. So, all right, very good. Well, thanks again, everyone. Thanks for joining us today. We'll go ahead and close, and I hope everyone has a great Tuesday afternoon. Take care.